All right, so we have here the valve. Hopefully you can already get it open. We have it, it's available on the Google Drive in the shared folder, SolidWorks. Again, we want to start out, we're going to look at the two lids that are already applied to our model. The objective of the lids is to enclose the computational domain, because what we need to mesh is where the fluid is going to be as it goes through the ball valve. So it needs to know where there's a start and where there's an end and where there's any walls that may be contained, that may be containing the fluid. So the lids are necessary to kind of cap and enclose all where our fluid is going to be located. So the lids are already a part of this model. We'll come back and use these. I want to show you how you can put your own in. If you note how these are made, these are done with a sketch, just a circle at that end and then extruded slightly. What we're going to do is we're going to use the lid feature in SolidWorks, which makes things really easy. All right. So if you haven't already, you need to make sure you add in flow simulation. So again, if you go up here to add-ins or under the tools menu, but go to add-ins and then make sure flow simulation is checked. You can do one side or both sides, but at least you got to do it at on the current active add-ins. And you should have this tab that shows up. And with that tab selected, we're going to click on Create Lids. And so with Create Lid selected, then you want to select planar faces where the openings are going to be. So we'll do one face here. And go ahead and green check that guy. And so I haven't put one on the other side, obviously, but I want to show you something here. When you're trying to enclose your geometry, you want to make sure that it is actually fully enclosed. And they have a check geometry button up here that actually check for that. So if we click on that, it shows all the things we have here, the lid and the fillet or the main body here. And we're going to check that volume. And we see here, results status failed. It's not watertight. So we aren't fully enclosed, and if we're not fully enclosed, it can't run the calculations. All right, so we can go back here knowing that the other lid wasn't placed on here, and we'll go back and create a lid. Again, selecting the same planar face here, and okay that, green check. And if we go back and we check our geometry, we should see that now we're successful, the geometry is okay. All right, so we are watertight in that case. All right, so that's how you can put lids on your model. I'm going to go back and use this model's original lids, because there's going to be things that change here in the future. The flanges on either end are going to get extended, as you'll see, and because the lids were associated with those ends, we won't have errors in the future. So anyway, you can use these lids just fine in your future drawings, but for now I'm going to delete them. All right, and we'll roll back down. All right, so lids are still there. So now what we do is just go in and we're going to use the wizard most of the way through here to set up our simulation. And we'll go ahead and call this project 1. And go ahead and use current. You can see here the current configuration is called the short valve, which is what we're dealing with here. We're going to work with some other ones that have some different configuration names. Go ahead and click Next. Obviously declaring our unit system here, which SI is fine, and you can see the units there and how they're defined. This is an internal analysis. We're not looking at external flow. It's going to be contained within our valve. And go ahead and exclude cavities without flow conditions. And you can see the other things we can do with flow simulation. We look at heat conduction, radiation. We get a time-dependent case, include gravity and rotation. But again, we're just going to focus on using the default settings here. Go ahead and click Next. Here's where we pick our fluid, and we're just going to be doing basic water, so that's a liquid. So go into liquid, scroll down, and add that. Flow type here, you see laminar and turbulent, so because we can expect possibly laminar or turbulent flow, we'll use this one. If you're doing with just laminar flow or just turbulent flow, you can select one of these other ones and help to focus in your model a little bit. But again, we'll just stick with the default here, laminar and turbulent. And don't worry about cavitation for now. Go ahead and click Next. We're not worried about thermal conditions. We're just dealing with the flow, so we can leave that as its setting and leave the roughness as the default. All right, here we can look at the kind of the initial conditions here, the pressure and the temperature. All right, basically STP there. And go ahead and click Next. All right, so this is the meshing. All right, so this is the basic mesh here at the value of 3. And basically you move it one way, you're going to get finer mesh, it's slower model. If you go the other way, you get more coarse mesh, but it'll run faster. But we'll leave it right at 3 is a nice place to start. Another thing we do want to do in this case, and again we'll come back here and talk about this in the next case where we'll change it, is we're going to manually specify the minimum gap thickness. If you go back here and look at our model, you can see inside there that this ball valve is partially open. And so we can see right there, we can see through there, and there's going to be this gap right here. We want to make sure there's lots of meshing elements in that spot so it can resolve any gradients that may be in the flow. And so we're going to specify this minimum gap size as 0.04 meters. Leave everything else as the default settings, and we'll go ahead and finish there. All right. So what it does is it creates our domain. It doesn't really show you the meshed version, but you can see the domain is going to be contained within that box. That box contains everything that goes through the opening, out the exit, and ultimately through that ball valve. We can turn that off. We don't really need it to see it, so we'll go ahead and right-click on computational domain and hide. All right. Now what we need to do is set our boundary conditions. All right. So we're going to go over here to boundary conditions and right-click. And we'll go insert boundary conditions. All right, you need to select our first face. So we're going to select our inlet face here. But remember, this is basically a three-dimensional lid. And so we want to make sure we select the face that's on the inside where the flow, or if there's water contained here, where the water would actually touch. So we're going to right-click on that surface and select Other. All right, that'll allow us to pick stuff that's inside there. And again, we want to pick the face that's on the inside. So if we turn this sideways and we zoom in here, if we hover the first one, that's clearly not that face. That's the face, but see how it's on the outer part. It's not going to be the part that's touching the fluid contained within the valve. This is the one we want. So we'll go ahead and select that one, that surface. All right, and it looks like it didn't take, oh, there it goes. My computer's just being slow. And we're going to do an inlet velocity. So just select velocity there, inlet, and go ahead with 1 meter per second. And go ahead and click OK. So this means that at this point in our valve, we're going to have 1 meter per second flow entering into that space. For the other boundary condition, we're going to come to the other side, and we're going to right-click and insert boundary condition. Again, right-click on that surface there, select Other, and make sure you get the right face. We want the one not the one on the outside, we want the one on the inside. So select that one. And we're going to go for our outlet. We're going to do a pressure opening and go with static pressure there. And you can see it's kind of STP conditions there. So we'll green check there. So we have our boundary conditions defined there. Go to our goals. Our goals is the place where we're going to define what we want it to record. And in this case, we're looking at the loss through our valve, and it's specifically the pressure loss. And so that's what we're going to look at here. And so we need to define the goals at both the front and the back surfaces. So we'll right-click on goals, and we'll insert surface goals, because it's going to be the inlet surface and the outlet surface where we're going to look at the pressure that we're interested in. We're interested in the total pressure. Right, so it's kind of hidden there, but we're looking at the total pressure, and we'll take the total average pressure. So we got minimum, average, maximum, and that's bulk. All right, so we're just going to go with the average total pressure. And again, the faces we want is the inlet and the outlet. We can go and we can right-click and select Other and try to do that again, but we've already done that, and we can use our previous definitions for the inlet velocity and the static pressure to do that. As you can see, if I just click on them, I only get one or the other, so hold down Control, and you can select the other one and get them both. We also want to make sure we create a goal for each surface, because we want to look at the pressure at just this surface and the pressure at just this surface. And so we'll select that one. All right, and we can green check there. And you see we end up with our 2 goals over there. All right, so at this point, I think we have everything defined. So we can go ahead and run the calculation. So come up here and just click on Run. And we're going to do a new calculation, use all the CPUs that we have, and go ahead and run. And we'll watch this as it meshes the geometry. And now it starts doing its calculation. You can follow along what it's doing right here. You can follow calculation progress over here. And this is going to pop up here. So it says the vortex crosses the pressure opening. All right, so we have the pressures here, and so it says there's some type of vortex going in and out of this pressure opening. We don't have constant flow exiting out that point. It's a vortex, and that is not a good place to be in your modeling. So we have a problem here in that the flow wants to swirl at this point, but we don't want to calculate our pressure based on the swirling vortex that may be there. All right, so what we need to do is we're going to need to extend out, or basically connect a pipe to the exit of our valve, and might as well just do it on both sides to make sure we have a uniform flow going in and out without any type of swirling. All right, so to do that, we're going to clone our project and repeat this with pipes that are attached to it. So if we come up to Clone Project, and click on Clone, and let's call this Project 2. And in this case, we're going to select our new configuration. So instead of the short valve, we're going to go to the long valve. And so make sure just that one's selected. And click OK. And you're going to get two warnings here. It says, the settings have been changed. Do you want to reset the computational domain? Well, because it's now longer, yes, we do want to reset. We don't want to just model that shorter valve. And then, yes, we want to start the computational over. We want to reset the computation. We don't want to use old results. All right, so you can see here now the lid's still out here at the end, and lid's still over here. We still have our boundary conditions defined. We still have the total pressures defined. So we're ready just to go ahead and run with this new model. Again, it's new calculation. Everything else is set up the same. And this time that it's running, we're going to watch for this guy to become colored, and then we can use that to actually preview what's happening. So we'll click on that, and we'll go to, you have to figure out which plane it is, but plane 2 is going to work well here. And now you can actually look at the pressure profile change as it's calculating. Right? So you can see as it continues to change, basically it starts out at an initial pressure, initial guess, and it continues to iterate until it reaches steady state. And you see high pressure upstream, low pressure downstream, right? High pressure drives the flow to lower pressure. And we see the different pressure differences across the partially closed valve here. Right. So it's going to continue iterating here, I believe, close to 100 iterations before it's done. All right, so now we're done, so you can go ahead and close everything up here. Right. If we want to see the results here, we can look at the results and expand that. And the first one here is cut plots. All right, again, if you don't have to look at these. Some of these, I think you actually need to show me a contour for the homework. But we'll get to that point a little bit later where you get the pressure values. But I'll show you some plot creations here first. So if you, under the results, you can insert cut plot. And go ahead and keep it on plane 2. If plane 2 doesn't show up here, just click this box and hit the flyout menu, and then you can select plane 2 from there. And plane 2 shows up, so that's good there. I'll go with contours and vectors. The contours will leave as pressure, and just leave those as it is. And actually, let's just change it to velocity here. We'll do velocity in the x direction. And we'll do velocity here for the vectors. And for the vectors, we'll do the spacing. Change that to 0.012. And this is just so it looks better. I mean, these are pretty arbitrarily depending on what you want to see. Arrow size will be 0.02 meters. And go ahead and click OK. All right. And now you should see your contour, right? But it's not there. Oh, we can see a little bit in there. So what happens is the plot's in there, but it's inside of our pipe. So the way to do that is come up here to transparency, and if we just up that to around 75, we can see right through and see our velocity profile through there. Now, again, if you want to get down that face nice and cleanly, we can go to the top face there and see it much better. All right, but look at the vectors here. Hopefully you can see this pretty well. We got vectors moving to the right toward the outlet, but then we have vectors down here into the wall moving back toward the inlet. And this is our vortex that was caught in the short valve case, whereas in the long valve case, if we zoom out here and look toward the end, we can see that all the vectors are now going out the outlet. There's nothing actually circulating down here. So now we have a good outlet conditions, and we can get the actual pressure drop that we have there instead of having basically the velocity changes that would be affecting the pressure result. All right, so it's a nice cut plot that we can view there. Let's do some additional kind of tweaks to this. So what we'll do is we'll come in and right-click on our cut plot. We're going to edit definition. So right-click on our cut plot 1, edit definition. And down here, click on this button here where we have the min and max. We can adjust those. And we'll leave the maximum where it's at. We're going to change the minimum to 2 meters per second. So this means that anything below 2 meters per second is going to look the same as something at 2 meters per second. So go ahead and click OK. And we can see all those smaller arrows get a lot bigger. So basically you can see them a little bit better, a little bit more easy to visualize. Another thing we can do to really look at, where's the flow going toward the inlet, where's the flow going toward the outlet. If we double click on our palette bar, it'll bring up our little dialog here. And we'll change the slider here. Instead of being 10, drop it down to 3. So we basically have 2 colors, blue and red. And then we'll do the maximum here as 1 meter and the minimum at -1 meter per second. And go ahead and click OK. And now we can see clearly flow going, at least the X component of the flow is going in the positive X direction when it's red and positive or negative X direction when it's blue. All right, so again, just a nice visualization possibility there. If we want to look at something else, we can come back in and double click on the bar again. Instead of doing velocity in the X direction, we'll come down here. Let's go to add parameter and come into loads. And probably won't already be selected. You have to come in here and you can select total pressure. In this case, I'm going to deselect relative pressure, but select total pressure and click OK. And velocity X will still show because that was the last one you selected. But now total pressure should show up. And go ahead and select total pressure. Now we're going to up our levels back up to around 30 or 230. All right, so we get 30 there. And now go ahead and click OK. And now we're looking at the pressure contour. All right, so the color contours are the pressure, and the vectors there are still the velocity vectors. So now you have kind of 2 pieces of information shown at the same time. So we got this high pressure up here. All right, see a big pressure drop here from, say, orange to green here from around 113 kilopascals to green, which is 107 kilopascals. And we have this low pressure region in the middle of the vortex where we expect it to be. All right, so it's a lot of information we can see now. All right, but let's get these pressure values. So that'll be under our goal plots here. So we'll come down and we'll insert goal plots. And we want to see all of them. We want to see both pressures here, that we pressure at the inlet, pressure at the outlet. And if you're going from the tutorial says just click on the green check mark. And if you do that, it's not going to open Excel automatically for whatever reason. So what you can do is just come back in here when you're creating the plot. Just come down here and click on Export to Excel. And it'll get right in there. All right, and here we can see the values. Here's the low pressure, so this is the outlet, and here's the higher pressure, and that would be the inlet. And it gives you some other information there too. But these are the 2 we want to be working with. All right, so we're going to work with the calculator that's within SolidWorks to figure out what our loss coefficient is. So if we come up to our flow simulation menu, and then under Tools, go into Tools and then Calculator. So Flow Simulation Tools Calculator. And it opens up kind of like an Excel spreadsheet. And if you just come in and right click here on cell A1, and we're going to do a new formula. And we're looking for pressure, so obviously we would go under pressure and temperature. And we're looking at the total pressure loss. So what this does, it'll ask us for the things we need to calculate that K value, that loss coefficient for our valve. So go ahead and click OK, and it's going to give us the total pressure loss. It needs to know the total pressure at point 1, total pressure at point 2, the density of the fluid and the velocity of the fluid, and those are all the things that are in that loss coefficient equation. So let's put those things in here. The density, you're going to have to plug this in, just knowing the density of water at the temperatures that we're dealing with. So 198.1934, and you can see the units get put right in there for you. And the velocity we put in was 1 meter per second. Now the pressures we need to get from our Excel spreadsheet, so we'll just go back over there and just go ahead and Control-C copy and go back in here and we can paste and copy and paste. And you can see it calculates right out for us. So we get a negative value here because the total pressure at point 1 is thinking about an upstream pressure. That's the higher pressure. And so we can actually just swap these around here. I'll move this one over here, copy and paste these back into their spots. All right, so then we come up with a positive value there. All right. Now that's all well and good. What that gives us is the loss coefficient, not through the valve. That gives us the loss coefficient through the valve and the extensions or the pipes that we added onto it. So we want to find out what the loss value is for a piped area, and then subtract that off this value to come up with the one for just the ball valve section. So we'll go ahead and save this, and you can save it wherever you want. We'll call it ball valve. Again, as long as you can go back and find it. And reference name. Okay, so go ahead and close that guy out. And yeah, you don't need the Excel spreadsheet now. All right, so what we're going to do is we're going to do the same thing we've done before when we went from the short valve to long valve. We're going to clone the project. We'll call it, go to project 3, and we'll select the 0 degree valve, long valve. You can go ahead and green check. All right, and yes, we want to reset the domain, and yes, we want to start the computation from the beginning. Notice the valve angle. Right? The valve is now fully open, and if we can look down here, look down the centers, or rotate it around, you should be able to see all the way through. Right, so we have a fully open valve now. All the boundary conditions are still the same. The goals are still what we want, so all we have to do is come up and run it. Oh, correction. Before I get too far into there, stop that. I'll see the results. And actually, it's not a big deal. But basically, if you come back into right-click on input data and the initial mesh, all right, I said we come back to this manual specification of the minimum gap size. Basically, the gap the whole way down is going to be the same because we don't have a partially closed valve now, so it's the same size the whole way down. So we'll just leave that and let it automatically specify what that minimum value should be. So go ahead and click OK on that, and now we'll go ahead and run it. Again, if you want to view, as expected, if this is going to be just a uniform cross-section the whole way through, the pressure drop isn't going to be nearly as much as it was between the partially closed valve. So you can see those values are very close to each other. And it's done after 57 iterations, so we can close out there. We're interested in our pressure values, so we can come back in and go to our goal plot and go ahead and export to Excel. All right, so we got our 102 kilopascals and 101 pascals. or kilopascals. And we're going to take that back into our calculator. So let's come back in here and go flow simulation, tools, calculator. And we'll open up the file that we were using before. So you can either come back in here to recently used files or open it up and find it. And it looks like it doesn't like the spot where I had it before, so we'll just go open and find it. I saved it in the downloads folder. So there's ball valve. Click on open. All right, so there are all the values there we had from the previous time. Now let's add in the stuff that we just calculated. So we'll copy the values we have from the Excel spreadsheet. I'll just copy both of those, and I'll paste them in here. And we'll copy this so we have it saved. So that's our 40 degrees pressure loss. And let's put these guys up here. You can copy and paste them up here. A little kind of fun, easy way to do this is you can add a relation. And now you can see that kind of the cursor changes. Just click on the cell that we want to add to there. So you can see it's equal to B5. And you do the same thing here. So, click on the name at the header of the row. Add a relation. Click on the lower one. And you can see the final value there for just the pipe. Now it does go through the valve, so you do have a little bit of loss that's included from the valve just being wide open. So technically you probably should just pull the pipes off and connect them and look at that. But this takes off, you can see 0.4 off the 25.8, so about 25.4 for our loss coefficient. All right, so you guys can be able to do that with your project. If you want to find some additional details, I gave you a Reynolds number for your project instead of a velocity. So you can calculate that using the Reynolds number. And I think I told you where to look in the other tutorial how to use that, or you can just do it by hand. All right, and with that, I leave you with I hope you have a good day.